Okay, great. Today we're happy to have Anna and me talking about very cool spectroscopy. Okay, yeah, so I'm going to start talking about ultrafast spectroscopy and ultrafast physics in general. So the first part of this is sort of a general overview of this field and the experimental techniques that are sort of all grouped under ultrafast. I'll sort of specifically focus in particular on ultrafast or time resolved ARPAs, and I'm drawing this from all of these reviews, which we can tell that this field has sort of grown very quickly in recent years by the number of reviews that have been written just in the past few years. And then I will definitely talk about this first paper where they use time-resolved ARPAs and time-resolved X-ray diffraction techniques to directly measure the electron-phonon coupling in an iron-based superconductor. And if time permits, I will also talk about the second paper looking at monolayer TMDs, excitons in monolayer TMDs, where they, again, can use these time-resolved ARPAs techniques to directly image the exciton wave function. So, yeah. Okay, so, but I guess also to tie into what Zhu-Xi will be talking about, we'll see that broadly, while these ultrafast techniques make use of a broad range of electromagnetic frequencies and sort of look at a wide range, take advantage of laser pulses on a wide range of timescales, that sort of what we really care about is this terahertz, like IR range of frequencies where a lot of the interesting behavior in various materials happens and can be investigated. So I'm going to be talking about sort of this ultrafast side of things, and then Zhu-Xi will talk about some more stuff about spin liquids and terahertz spectroscopy for spin liquids. All right, so for now, I'm going to not use the slides. So first, what do I mean by ultrafast? So this term broadly kind of encompasses explorations of light matter interactions at the shortest timescales that we can engineer. So this can range from attosecond physics, like was given to like attosecond physics as like the Nobel Prize this year was awarded to physicists and chemists who deal with physics and dynamics on the attosecond scale, which is 10 to the minus 18 seconds. But ultrafast also goes to see in the papers I talk about that we hear often about femtosecond all the way up to nanosecond. So there's ultrafast encompasses an extremely wide range of timescales. But why do we care about sort of femtosecond in particular? This is because sort of femtosecond and picosecond, around 10 to the 15 to 10 to the 12 seconds, minus 15. These are the timescales on which sort of the fundamental interactions in materials are happening, like electron-electron interactions, electron-phonon interactions. And so if we can probe the dynamics of our materials with this sort of time resolution, we can get insight into sort of what are the actual underlying mechanisms that give rise to the emergent phenomena that we see in a wide range of condensed matter systems. So I will note that ultrafast is really referring to the timescale of the dynamics that I'm interested in, or the timescale of like the laser pulses that we are working with, rather than the frequency of the light. We'll see that the frequency of the light can range from microwave terahertz, like IR, all the way up to X-rays. Okay, so what are the main experimental techniques that we use to look at materials on these timescales? So the main sort of the unifying theme of all of these experiments is the idea of a pump probe experiment. So the idea is pretty simple. You have your sample. It could be a 3D material, 2D material, and you're going to send in some pump pulse, laser pulse. Usually this will be some like IR pulse. And you're sending this in to excite your sample somehow in some targeted way, to create some non-equilibrium conditions. And then with some time delay, you send in your probe pulse, which will actually tell you about sort of what's happened in your system after you excite it. And by looking at, you could look at the absorption of this probe pulse, or it could be some X-ray scattering experiment, or as you see, it will be, we might have some ARPES type setup happening. By varying the time delay between your pump pulse, where you're exciting your sample, and the time at which your probe pulse reaches your sample, you get sort of a movie of what's happening in your system. And you can plot, for instance, if we're looking at ARPES data, we might have or just some optical like absorption experiment. We can plot, for instance, the intensity of our probe signal as a function of time, and we'll get in general some data as a function of time, which we can glean something about what's happening in our sample. So that is very vague, but this is like the model for all of these experiments, and you can replace this pump pulse with sort of something targeted to excite your sample in exactly the way that you want to for what you're trying to explore. You can sort of substitute what exact frequency and energy you have for your probe pulse to be sensitive to the kind of dynamics that you're interested in. And of course, the sample might be sort of any condensed matter system that you're interested in.
Question?
Yeah.
The pump field is typically spatially uniform or spatially focused on some?
Yeah, so that's a good question. It depends. So usually at the moment, it's tends to be hard to like focus these very fast pulses, also like in a small spatial area. Oh, yeah, did you go in?
Particularly, there is this thing called diffraction.
Yes.
Yes, and usually, for example, for terraform sample, sometimes the speckle is larger than your sample, for example, in stories sometimes, but here, but the terraform pulses can be larger than your larger than the entire sample. So it's pretty hard to do. One thing that one can do to improve on this scenario is to apply the pulse to the tip, and then use the tip to focus the pulse yourself.
Yeah, so it's exactly like time resolved STM, which is sort of a nascent experimental technique. Yeah, so people are trying to get more spatial resolution, but for everything I'll talk about today, it's generally uniform over the sample.
And also sometimes I've heard the concept called near field.
Yeah, I guess I'm not sure what the context yet. Okay. So the way that this pump probe idea is sort of the archetype for all of these experiments, but you can substitute in sort of a lot of different techniques in here. So for instance, yeah, you might just have like some more conventional optical sort of probe experiments where these are sensitive to the dielectric properties of your material. And by sort of using them in this pump probe manner, you get some insight into the dynamics of the optical properties of the material. And here, yeah, you can get up to sort of femtosecond, tens of femtosecond resolution in the time domain. Something I'll touch on briefly are scattering probes. So this just like regular X-ray diffraction, equilibrium X-ray diffraction, you can send in an IR pulse to excite your material. This might induce some sort of phonon excitations, and you can send in sharp pulses of X-rays and get dynamical information about the structural properties of the material. And then, yeah, again, have the femtosecond resolution. And then the other one I'll be talking a lot about is time resolved tests. So again, you're performing a pump probe experiment, but you also have this like within an ARPES setup. So you send in again your pump pulse, excite your material, and then you send in some UV light to photo excite kick electrons out of your material, and you have some detector, hemispherical or whatever, that can measure both the extract the energy and the parallel momentum of your electrons, and you can get information about the momentum dependent energy of your system, but also, you know, again, because we're doing it in this pump probe way, we get dynamical information about how occupation of different energy levels might change, relaxation dynamics, but also if my original excitation was strong enough to actually change the properties of my band structure, I can get dynamical information about that as well.
Sorry, but all of this just measuring intensities.
Yeah.
Nice.
And then, as G brought up, there's also a move to add spatial resolution in addition to fine scale temporal resolution to these sorts of experiments. And so we can have we can also have time result, like scanning tunneling microscopy. And so, but this is very cutting edge, and still the challenges of this direction are still being worked out.
Which group is with?
I'm not sure. I have to go and look back. But I will say the first 3 reviews here go very in depth on who's doing all of these. All right. So now that I've told you about the sort of techniques used, what can we actually use them for? And what do people use them for? So as I hinted, there's 2 sort of main regimes that we can think about the light matter interactions in these sorts of experiments falling into. So the first one is so-called weak excitation regime. So in this scenario, the pump pulse that we initially send in to excite our material doesn't fundamentally change the energy landscape or the couplings in your system. You can think it's just sort of maybe exciting some quasi-particles to some previously unoccupied states. And then we want to use our pump probe experiment to see what these excitations are and see their relaxation dynamics back to the original equilibrium to gain some insight into both the original equilibrium state and also the quasi-particles in our material. So like I said, pulse pump and so we're interested in this regime for looking at quasi-particle dynamics, lifetimes. We also care about if we're in some symmetry broken state, or about if we can switch our system into some other minimum of its energy landscape. So for instance, switching of the magnetization in some material. And then also, of course, with equilibrium ARPES, you're limited to imaging states below the Fermi energy that are occupied in equilibrium. But this method, where we first excite our system and then we image the band structure, allows us to access higher energy unoccupied states. But the second regime is the strong excitation regime. So, as we might guess, this is where our initial excitation is strong enough to fundamentally change the properties of your system. It might drive it through some phase transition. And in this way, people are sort of interested in these ultra-fast light matter interactions in ultra-fast experiments because they not only provide ways of looking and exploring the properties of materials, but also engineering properties of materials. And so this comes about. There's examples of light-induced superconductivity. And Floquet engineering, taking advantage of the periodicity of your pump probes that you're sending in. So you can get novel Floquet block bands in your solid. And then also you can have interesting non-equilibrium phase transitions that you can't get otherwise. So for instance, there's a famous example of being able to demagnetize a magnetic material on super fast timescales through the application of this sort of ultra fast laser pulse. So this is very broad overview of what's going on, and by no means an exhaustive one. But want to sort of move on now to talking about specific experiments, so we can get some idea, some explicit example of how these methods are used to tell us interesting information about condensed matter systems. So first, to do that.
What's the main difference between the two? Is that just the intensity of light?
Yeah, it can be the intensity. Yeah, although say, yeah, it will be system specific in general. Like what is the from where you draw the line, and say also there's sort of details where there might be some polarization, like it might also depend on some other properties of the light other than the intensity. But yeah, it'll be very material specific.
Probably the couple of strands on flat method. Yes. The first case is a clean coupling, the second is an automatic coupling with strand.
Yeah, but what determines that?
There's a volume, in the cavity system, the volume of the cavity will determine the light matter coupling strands, and also the frequency of the light. So the intensity property is related to the number of photons, but not related to the mathematical coupling. I'm not sure.
I think maybe one interesting example for either in between one and two is there are materials where they're like, you can imagine these going to documents like and that'll so breaking mass gap that's proportional to the intensity of the light. But in principle, for even very small intensities, you go from a second metal to the so even for small intensities kind of changing.
Okay, so yeah, so the experiment I'm going to talk about before I jump into the specifics of the setup, I wanted to dive a little bit deeper into time-resolved ARPEs specifically, because this is the main technique that they use in addition to X-ray diffraction, but I think, but I'll go more into detail on the ARPEs. Okay, so yeah, so a few weeks ago, we already had our session on equilibrium ARPEs. So I won't go too into detail on the parts that are like the same between the two techniques. The main elements of time-resolved ARPEs that are different are this pump-probe approach, and there's some sort of specific technical difficulties to this method that arise because you're working with ultra-fast like laser pulses. But everything else, like regarding sort of the detection and the data analysis, the extraction, the data from your photodetector is very similar. Okay, so yeah, so this is sort of gluing this technique, you glue together ARPEs and pump probe type experiment. So usually, like I have here, we have initially some IR pump pulse, which gets sent in to our sample, and then some subsequent probe pulse, usually in the UV, to be energetic enough to kick your electrons out of your material, is sent in to sort of glean information about the momentum and energy and the occupation of your bands. So yeah, so setup is just this up here. That's the main idea. And by, like I said before, by varying the delay between your pump pulse and your probe pulse, you sort of get an idea of what's happening on these like femtosecond timescale. So what are the advantages of using time-resolved ARPEs versus sort of an equilibrium method? So mentioned, it grants us access to states that are not available in equilibrium. So unoccupied states, but this might also be, if we're in the strong excitation regime, just states that are not available in our system unless we have this very sharp initial excitation.
So you assume your sample is at a very, very low temperature, so it's.
Yeah. Although it doesn't have to be like dilution fridge cold. In fact, for the paper I'll talk about, they take data at two temperatures at 20 Kelvin and 90 Kelvin. So yeah, it doesn't have to be too cold. And because we have this femtosecond scale resolution, we can actually sort of study elementary scattering processes. We can study how our excited state relaxes back down to equilibrium, but in a very sort of detailed way that allows us to pinpoint sort of what are the mechanisms behind this relaxation. So direct access to elementary scattering processes. Yeah, and this, we also, yeah, so we have unoccupied states and non-equilibrium states. And we have this window into specific interaction mechanisms. Okay, so these are sort of the benefits or the advantages of this method, which motivate us to want to use it. But it has sort of technical challenges that come along with it. So a large one, is it gives space charge. Distortions. So this, so what's happening in our PES experiment is after you've excited your material, you send in your UV light, it kicks out electrons at some momentum. They fly through space to your photodetector, and then you detect them. But you know, it's key that the initial distribution as they get kicked out doesn't get distorted along the journey from the material to the detector. But what can happen if you have too high of a density of photoelectrons that have been excited from your sample at once is that their Coulomb repulsion actually becomes important as they're traveling in this cloud to your detector, and they can sort of their distribution, initial distribution can become widened and sort of blurred by the Coulomb repulsion effect. And so this is something to avoid if you want good data, if you want to be able to clearly read out what's going on in your sample with accuracy. And so one way to get around this is to lower the intensity of your laser pulse. So you just have fewer electrons being excited at once. But this means that you have to do more experiments to get your data. It also means you might not be reaching the regimes that you care about for your experiment. So another thing you can do.
Is it possible to theoretically map it back, or is that no one can do it?
That might be an extremely chaotic, like.
I understand it's hard, but like,
I mean, I don't think. I'm sure that there's probably some like maybe there's some people looking into like a cleanup algorithm for our PES data for this, but at least it seemed like everyone just wants to avoid this at all costs instead of dealing with it in post-processing. So I imagine it's very hard. Yeah. But so you can, yeah, so you can mitigate this with lower laser intensity. But if you don't want to do that, you can also, well, you can mitigate the possible negative effects of lowering your laser intensity by increasing the repetition rate of your laser, the rate at which it's actually sending out pulses, so that you sort of make your data taking more efficient. But this and higher repetition. And this comes along with its own issues, because if you have a very high rate of repetition, you're sending in these pump pulses very quickly. Your system might not have time to equilibrate in between when you excite it. And so you'll get sort of heating of your sample very quickly. And this also doesn't lead to good data. So you also have to sort of optimize the repetition rate of your laser. In any case, I get the sense that repetition rate is not something that's necessarily easily tunable in these laser systems. And then, yeah, so you also want to minimize heating. And third challenge is that we have a trade-off just by fundamental uncertainty relation between our time resolution and our energy resolution. And so if we want to have very fine-grained dynamical information, this might be at the cost of having very fuzzy data when we're actually looking at the energies involved. And then, so this sort of trade-off is captured in the bandwidth of your laser. So wider laser pulse, finer energy resolution, sharper laser pulse, finer time resolution. But this bandwidth considerations also sort of have interplay with these other considerations just on the level of like laser engineering.
What about the earlier thing about the high repetitions and the heating? Why not just take longer?
Well, if you do take longer, because often you have to do these experiments in like synchrotron, like with like light from it just costs money. Yeah. Yeah. And then. Yeah, so all of these mean that there's a lot of complicated considerations an experimentalist has to make when choosing sort of right laser frequencies, the right bandwidth for these lasers, like various things that I know nothing about. So this means that, yeah, and so oftentimes there has to be concessions made, which means that at the moment, time resolved ARPES data can be fuzzier than sort of equilibrium ARPES data. But I think we'll see that it's still very powerful. Yeah, okay, actually, another thing that I didn't mention in these challenges is that you also want to have your probe light be at the right energy to be able to actually explore all of the parts of the Brougham zone that you care about, because there's you need sort of enough energy in your photon to actually like kick your electron out of your material. And so this also means that the constraints on laser energies also put constraints on the sort of physics that we can explore. All right, so now I will go on to the paper, and I'll put slides back up. And I think in the interest of time, I might only talk about the first paper, but I would highly recommend the second paper as well. Okay, so what is the setup of? So we are investigating iron selenide, I think. Yeah, with FeSe, which is one member of the family of iron-based high TC superconductors. And we're going to be investigating electron phonon coupling strength. And so this is this Gerber et al. 2017 paper. So we're investigating we want to measure directly the coupling between electrons and phonons in this material, because we want to know why it becomes its critical temperature is very high, and one mechanism that we know for superconductivity is phonon-mediated superconductivity. And so previous experiments attempted to measure this electron phonon. Okay, so I guess one way of quantifying the relevance of phonon-mediated superconductivity as a mechanism in a material is looking at how strongly electrons couple to phonons. And specifically, we can define this quantity called the deformation potential. Which roughly the change in your in the energy of your electron with some given deformation of your lattice. So we'll see this is some change in the maximum in the average energy of some given electron band over some displacement of the selenium atom in this material caused by a phonon, a coherent phonon excitation. So yeah, so said previous experiments attempted to measure this, but they had to do it in a very indirect way using sort of regular not time resolved ARPES data, which involves you can extract information about interactions in your material from ARPES, but oftentimes it requires some non-trivial assumptions about the structure of interactions in your material to be able to sort of extract anything. And the goal of this experiment is to use time resolve techniques to be able to get rid of all of those assumptions and directly measure the coupling between the electronic and the phononic degrees of freedom. Okay, so the setup again is this pump probe setup. So we have a thin film of our iron selenide, which is 60 unit cells thick. On top of this substrate, which is, I guess, my strontium titanium oxide. And again, we're going to send in some IR pump. Specifically, the peak energy is 1.5 electron volts. And then in this case, we're going to be using two different probes. So first, we're going to be using an X-ray probe to in a X-ray diffraction experiment to look at the dynamics of the lattice, to actually directly look at the phonon excitation. And there's also going to be a UV probe, which we'll use to do the ARPES experiment and get information about the band structure and the dynamics of the band structure. And this X-ray probe is hard X-rays at 8.7 kiloelectron volts. And the UV probe is 6 EV light, which is produced using the prototypical method in these pump probe experiments, which is frequency doubling using some birefringent crystal. Yeah, okay. So the procedure is, yeah.
A few stupid questions. So you mentioned measuring the band structure at this point in the superconductor.
Oh no, yeah. So at this point, we're above the we're above the critical. Yeah, I should mention that. So we're at ambient pressure, the critical temperature is around 9 Kelvin for this material. And so let's see, Kelvin, but the experimental temperatures will be 20 Kelvin and actually 180 Kelvin. Alright.
This would be the TC 9,000.
Oh, this is just the temperature that we're running the experiment at. Yeah. Yeah.
Other
No, it's a thin film, so it's 60. It's about 60 unit cells thick. Yeah. All right. So
Is that 8.7 KeV or EV?
KeV.
Can you repeat what the function of the X-ray probe is?
Yeah, so we're doing two simultaneous experiments here. One, an X-ray diffraction experiment, time-resolved X-ray diffraction experiment, where we're going to eventually see this actually, like, see the phonon, like the oscillations of the lattice due to this phonon that's been excited. And then the UV light is for the ARPES experiment to learn about the electron, what the electronic degrees of freedom do.
I see. So that's going to be like similar to the expected phonon energy.
Yeah, that's a good question. So it's not. It's sort of but I think they're saved by the fact that the phonon response in this material is known to be like single mode. So there's like only one really strong phonon that will get excited by this light. Yeah.
I guess it's not like coherently excited, otherwise it would be like transparent to it.
Okay, so it is coherently excited through this mechanism called displacement excitation, which is fancier than it sounds. So I'll go into that now. Yeah, so first experiment is this time resolved X-ray diffraction. Yeah, and they carried out this part of the experiment at SLAC with one of their like linear light sources to be able to get these very sharp X-ray. Yeah, so the main idea here, yeah, so this is the data. So we perform this pump probe experiment, we send in our X-rays, and then we look at the intensity of outgoing X-rays to see the structural properties of material. And the claim is that this initial IR pulse coherently excited this particular phonon. So the A1G phonon. So what this phonon is just, you can see the crystal structure of this material up there, and the selenium atoms are purple, and this is just the phonon, the mode corresponding to them bouncing up and down. So the angle between the iron and the selenium changing, and so they indeed see that their X-ray intensity signal shows this oscillation at the frequency expected for this mode. So why does this IR pulse excite coherently a phonon? So you can think of it this way: this mechanism called displacive excitation. And so we can imagine that initially the selenium atom is in the minimum of whatever potential it feels, and it further, has some distribution of electrons around it, and our IR pulse comes in, and what it does is it suddenly makes this distribution of electrons very different, very non-equilibrium. So it might be really wild now due to this IR pulse. And so now the new potential, potential that the selenium atom feels is different. And it might not be at the minimum of this new potential anymore. It might be somewhere on the side. But because this pulse happened so quickly, it doesn't have any time to adiabatically go to the new minimum. And so what happens is that you get this oscillation about the new about the new equilibrium, but it will be damped as the system relaxes back to the old equilibrium and various other thermal processes. But this is the main idea of why we expect this IR pulse to couple in any way, excite in any way a phonon.
So the idea that the minimum is also determined by electrons.
Yeah.
So the electron is also oscillating. So the potential profile is also oscillating in time.
Or that because the electron distribution got changed extremely quickly by the laser pulse, that also the position of the new minimum changed too quickly for the selenium atom to sort of get there slowly. So instead it ends up oscillating around.
So both the pattern and potential.
Yeah.
So the higher pump is, but it is a pulse, but what's the time scale for the relaxation of the band structure?
Yeah, it's you can see this like time scale here. So on the scale of like
Oh, yeah.
10 picoseconds or something like that, eventually the oscillations just amplify.
It looks like the cleanest thing that exists in
It seems like pretty representative actually.
So how do I interpret the plateau for negative time?
Oh, so this is before you excite the you change this like distribution of electrons basically. So this is sort of what you would normally see in X-ray diffraction.
And why doesn't that go back to that same value?
Oh yeah, that's a good question. So I think in general, there's also for like a non-time resolved like an equilibrium X-ray diffraction experiment, you also see similar decay. Like you see this overall decay amplitude, just called the Debye-Waller effect. And from my understanding, it's just down to other thermal processes that are happening in your sample that eventually sort of kill your signal.
So it will eventually actually go back after if you wait longer.
I'm not sure.
Yeah. If you turn everything on.
Yeah.
Were you saying that even if you don't apply the IR pulse, just do the X-ray imaging, then it'll also slowly taper down, or because of the IR pulse that it's slowly tapering down?
I think it will also, even if you don't have the IR pulse, it will also slowly taper down.
Did that answer your
Yeah.
question? So apparently, the case unrelated to the IR, the growth, like, pump.
I mean, if you turn everything on, then it should just go back to the value.
Yeah, I think like if you turn everything off and restart the like experiment, it should definitely go back to
So it's the presence of a constant X-ray
Yeah.
probe that's
that also causes other stuff to happen in your sample and that interferes with itself.
I guess there's also heating the X-ray, which also happens with vibrate.
Yeah.
It's got at the ground.
And by subtracting away this background, because I think it's like a generally well modeled background, you can fit more precisely this cosine and see that these oscillations are happening at exactly the frequency that we would expect for this particular phonon mode. And so this is good evidence for the fact that we've coherently excited this particular mode.
Following this picture, what improved is also contains reaction tension. So how do you separate out the reaction tension from the phonon?
Yeah, so the idea here is that the electron interactions are happening on a very, very fast time scale, even faster than this femtosecond resolution. And so going forwards, the dynamics that we will see will be due to like electron phonon interactions. And further we'll see like that there'll be like the electron degree of freedom will also be oscillating at a frequency that's sort of locked with the frequency of this phonon mode. So
One last slightly stupid question. If I look at the graph, it seems to me that there are probably 10 oscillations per 2 picoseconds, and thus the frequency is about 30 terahertz. If I convert that to energy, that is probably 0.1 instead of the light frequency that you're sending in, which is 1.5. So why why is it such that there's no resonance as it seems? But, but there's clearly a optical absorption.
Well, okay, wait, so this peak is in just like Fourier transforming the data. So yeah, it's not necessarily, it's not like optical absorption data.
So the frequency of this oscillation is not necessarily the frequency of the photon.
It is.
It is
It is the frequency of the photon.
So the frequency of the photon is different from the frequency of the
Yeah.
of the IR.
Yes, because I think there's this sort of like intermediate step going on, which means that like I'm not coupling the light is not coupling directly to the photon. It's coupling to the electrons, which then have impact on the lattice structure, which gives me the photon.
Yeah, so you need an extra term for conservation of energy or something like this.
Yes, there is.
Yeah.
Yes, there is.
Sorry.
Yeah, I mean this like hot bath of electrons will like thermalize and will on longer timescales will also interact with like the collective modes and the phonons like in the system. But yeah, I think for that, and that contributes right to the noise in the tape.
I feel like this first plot is kind of gaslighting me that there's no orange curve.
Oh yeah, I don't know what that. I think it's the it's the key for the bottom graph and for the inside, but not. I think they're only plotting the blue curve. Yeah. Okay. And I'll note that they can extract the like absolute amplitude of the like displacement of the selenium atoms by doing some structure factor calculation where you assume that the selenium atom position is the only sort of important variable, and you can back out that displacement from looking at the intensity of the amplitude of your intensity oscillations.
How big is it?
Oh, yeah, it's about like a picometer or like a few picometers. Yeah, pretty small. Yeah, there's a plot. Yeah, so you can see on the, it's your right, extracted oscillation for the displacement of the selenium. Yeah. These are all for different laser intensities, the different curves. And they're just offset to like show you the different amplitudes. But yeah, but they're all they're not actually centered at the system. Okay, so we now have information about what's happening to our lattice. We know that this phonon has been coherently excited, and that it's been coherently excited with it has some particular frequency. So now we bring the electron part in with our ARPES experiment. And see, so here is the equilibrium ARPES data. Yeah.
In which sense are you saying that here the phonons are coherently excited?
Yeah.
What are the incoherent excitations of phonons? Is there an example?
I guess, you know, if we had some broader, like broader Fourier like transform signal, then this would be an indication that you have sort of excited like a lot of different excitations with conventional frequencies. From here we have this very sharp peak, so it's like we only have this mode.
The decay of the amplitude presumably also corresponds to coherent excitations.
Yeah, yeah. Yeah, these like other heating effects are examples of some incoherent things.
So we ask one last question, what's the point of choosing 20K and 180K?
Yeah, that's a question. I think to demonstrate that this data is clean enough at high temperatures, and that you can sort of get by like that this extracted data is like a viable measure of the electron photon coupling because it's valid. Very yeah, change if it changes. Yeah.
Yeah, maybe other, I mean, as a signal and scale, maybe as a thing can be signal. For example, I don't know
I don't know if it would be like if your X-ray experiment would be sensitive to that. Yeah.
Wait, how do you know that it's exploding the lab? Yeah, but yeah, you're seeing it. Oh, you're seeing the X-ray when you call positive. Exactly.
I'm gonna speed up so that it gives Zhu-Xi time to talk. But yeah, so for our physics experiment, sort of focusing on two bands, is like dz squared orbital, and then also the dxc and yz bands. And the data plot is from the time-dependent RPAS data, which is sort of slices that look like this graph at different points in time. Yeah, you're looking skeptical.
No, I don't understand. Sorry, I just don't know how to interpret this at first sight.
Yeah, so you can see sort of very broadly the features of this theoretic, like the sharp lines are the theory and the background is the actual ARPAS data. So you can see very broadly that you get some of the features. Yeah,
Quite broad.
yeah, quite broad. There's various like factors behind this, including like all of the challenges that I talked about, but also like there's all these like the matrix element between your initial state and your final state, like which means that the data can look very different from the theory that will take it on space for the moment. This is, I don't think, on a log scale.
So what's the white spot of green?
Yeah.
So you're supposed to be able to extract those curves from the density plot, is that?
Yeah. Well, so this is the band structure is calculated, I think, like DFT. It's not necessarily extracted from this data. But what you can do, is look at you look at sort of slices, constant momentum slices, and you get some energy curve, and by fitting the peak of this, you can trace out sort of what your band is. And that's what they're doing in this time series data as well. So they're looking at basically this type of this type of graph at different times. And looking at this sort of energy slice, constant momentum energy slice, and they have various methods of fitting these two peaks that they say are the contributions from these two bands that I pointed out.
This is now the time difference between the IR pump and the UV probe.
Yeah, so this data down here, yes, this delta T is the time delay. And these so this data again is for different laser intensities, and looking at the oscillations of the peak of the energy of these bands as a function of time. And then the graph on the far right is looking at a fit to the peak of fit to the band, the actual dispersion for various momenta, how that curve actually oscillates in time as well.
So one period here corresponds to, on the previous plot with the X-rays, like that time scale over which it took to equilibrate that, so, right?
Yeah, or this is, yeah, this is yeah, the distance between each of these points is like the distance is like a difference in the time delay. But my sense of like, yeah, it's done is that you don't necessarily just send in like a train of pulses, but you send in your pump pulse, and then that has some characteristic like repetition rate. But then you time your following probe pulse differently to sort of fill in the different times.
These are many different components.
Yeah. Yeah, so the system is not necessarily equilibrating in between each of these, like in a period of this oscillation.
That's fine. I just want to know what is the relationship between the period of this oscillation and then the previous curve where the X with the.
Oh, so yeah, so this oscillation is the same rate at which the phonon oscillates. Like, but it's not it's a time scale like of the system's behavior, not of the like the repetition rate or anything about the experiment. That's like
The difference of time between the peaks corresponds to, the selenium atom going, 1 period in this potential.
But here you're comparing the chain of band structure.
yeah, so
This is the band structure
yes,
actually oscillating. So that's in that picture there.
yeah, so the X-ray experiment is telling us about the selenium oscillations. This
That's
experiment,
a way faster time scale than the oscillations of the band structure, right?
no, the key is that they happen at the same time scale because there is a strong coupling between the phonons and the electrons.
And I'm confused by that picture. That picture is kind of saying that the band structure shifts, and then during the time that it takes to shift back, the selenium atom oscillates many times. And that's what those small wiggles were on that plot before it stops wiggling.
I mean, there are 4 electrons there. How many electrons and they probably have different times there.
Yeah, sorry, like I think the electrons over there are the like electrons like surrounding the selenium, whereas the electrons here are the like conduction electrons of the material. Yeah.
Yeah, so I guess the fastest is core electron. Well, I guess the conduction electrons and the core electrons are really fast, but the conduction electrons kind of automatically small.
Yeah. And they're like overall like not just their distribution in the like regular band structure, but the band structure itself like changes on the time scale of the selenium. Awesome. So
In the band structure near
yeah, like this on this range of momenta that they're able to And yeah, so and so the punchline is that you can extract the frequency of this oscillation and see that it's the same as the frequency of the lattice oscillations. And then you can plug in sort of the extracted amplitude for the oscillations of the band and the oscillations of the selenium atoms and extract this directly, this electron phonon coupling. And it turns out to be much larger than expected from DFT or from, actually, I don't think there's previous experiments specifically on this material, but there were on its parent compound, and it's lower in that parent compound. And so only theoretical predictions that take into account electron-electron correlations actually agree with this measurement, indicating that sort of the electron phonon coupling itself is strengthened by strong electron correlations. Yeah, and so yeah.
Did they quantify the strength of the electron phonon coupling?
Yeah. So exactly by this formula where this is the amplitude of the band oscillations, and they found for this for one band, it was minus 16.5, and then for the other minus 13 for the XC band. And just to compare, the DFT estimates were minus 1.6 and minus 8.5 or something. So pretty drastic underestimations of how strongly the phonons and the electrons couple.
So those are just the variation of these amplitude of this oscillation over the amplitude of the oscillation. What if the frequencies of these did not match? You said that they magically match, but then they just not match.
Yeah, then there would have to be some other dominant interaction happening, but I think they expected that the phonon mode is has a very strong response, and it's there's kind of this one phonon that's very important, and so yeah, it was expected that you should, but good to verify that you see the same.
Is the whole field of iron-based superconductors now debunked? Because
well, strangely, in newer papers, not that many people cite this paper, and they talk about other mechanisms for other than the electron phonon coupling. So I don't know if that's because I looked at a bad sample of all these papers, but yeah, it's sort of interesting.
So maybe I'm not familiar enough with the books, but TC of 9 is part of ITC.
Yeah, I thought that too. Well, I think one thing is that the TC is very dependent on pressure in this material, and I think precisely for the fact that this electron phonon coupling is very strong, or at least that's the conclusion that they draw. And so you can, I think you can get it up to much higher. I don't know. Okay, I'm also not very familiar, so I don't know if 30 or 40 Kelvin is considered high TC as well. Yeah. But yeah, so at higher pressures you can. Okay. Oh yeah.
Why is the phonon spectrum so coherent even when this electron phonon coupling is strong? So
yeah,
the phonons are coherently said.
Yeah, I don't know the particular the actual physics explanation at the level of the structure of this material, but for some reason there is theoretical, there is some theoretical basis for it's like single mode response in this material. So for some reason this one phonon is like much easier to excite than like other modes. So yeah, but I don't have a good answer for that.
Sorry, I missed the actual number. What's the phone?
For the z squared dz squared band, it's 16.5. The minus sign is because they're actually like shifted in phase.
60% what?
There's oh yeah, it's I guess joules per meter, or or sorry, like not exactly. Let me pull it up.
Energy divided by.
Yeah, it's milli electron volts per picometer.
Somehow for interviews, scale.
Yeah, I guess not. Okay, so I guess saying is not necessarily that. So the single mode response doesn't necessarily necessitate this strong electron phonon coupling. That's sort of an independent property.
Near the delta, does the delta A depend on the number of excited bonds? Is it proportional?
Yeah. So that's something I skipped over, but they actually extract these delta E and delta Z from looking at the amplitude as a function of the laser intensity, and like extracting a linear fit to this data. So I think this so the response definitely is, like, it's in this linear response regime where the response, like the amplitude of these oscillations will depend in general on the intensity of the initial phasor. Yeah. Okay. Yeah.
I will finish within 30 minutes. Multiple questions. Most of my talk will be about theory, which is relatively simple. I mean, compared with experiments. Originally, so my topic will be, let me use the board in the middle. This is the board. So my topic is 2D coherent spectroscopy. Terahertz. Originally, I chose this topic because I heard so many rumors about how to use this thing to detect spin liquid in topological water, and I got very excited. But after Googling a little bit, I figured most of the papers are theories. There's no single experiment paper using this technique on any spin liquid candidate materials. There's only some papers on conventional things, conventional spin waves and magnons. This is a paper on spin waves, which I will talk about today. And this is a paper on transverse field Ising model by John Hopkins group. It's a theory paper. They consider this domain walls in the spin chain, which is also deconfined. They view it as spin-ons. And then also talk about two theory papers on Kitab spin liquid and Tor code and Vecna. Yes.
Is there nothing proof as experiment? Or
No, it's an experimental group, but doing a theory work. It's Peter Armitage.
But they haven't followed up on actual proof?
In the paper, they mentioned such experiments are on the way. That's a May 2019 paper. There's no experiment yet. But then later in June 2021, there's a paper from the same group on Kitab spin liquid material, but not this one, but with just the usual linear spectroscopy. So you can view it from different ways. If you're optimistic, you would think, okay, they did this thing for like linear spectroscopy for Kitab spin liquid. Maybe the next step is the nonlinear one. If you're pessimistic, maybe something is wrong with this Ising model, and they step back and look at the linear thing. I don't know. We just need to wait. There could be various subtleties. This is basically calculating higher order susceptibilities, nonlinear susceptibility. So the signal would be proportional to the perturbation, the magnetic field. So the higher order you go to, the weaker the signal. So you need a very strong field, which could be hard to generate. And if the field is too strong, you may break the phase. Like you'll go to some other phase. So there could be some subtlety there. But because of the limited number of papers on these things, I don't have a complete understanding of what are all the subtleties. So I will. Okay. Linear spectroscopy. Type 1 of omega. When you have fractionalized excitations, you create a, for example, create a spin-outs in pairs. You typically get some broad spectrum. Each pair of spin-outs, so this is basically a convolution of various things, right? Each sharp peak is like say centered at frequency omega. It's summation of lambda minus k plus lambda k. Lambda k is a dispersion of the single spin-out at momentum k. So this broad continuum is basically describing how the energy and momentum can be shared between the pair of spin-outs. And this, well, it may be a good feature of spin-outs in 1D, but in 2D, there are a lot of other things like disorder, finite lifetime, and other things. So when you see a broad continuum, you cannot really conclude that you have a spin liquid. So you want something sharper. What they have is basically what that 2019 paper proposed is instead of doing a one-dimensional thing, you do a two-dimensional color plot. You have two frequencies. You perturb the system with some frequency, with some light, and then detect it with some other light. And then you have two frequencies. You can do a plot. You still have a convolution. You have the congestion basically along the diagonal. It's very bad drawing, but then you can see the intrinsic spectral properties such as the line width, the lifetime by looking at the anti-diagonal direction. Okay, so I'm going to discuss the setup of the transfer to leading chain paper. So setup is very simple. So you have your sample here. At time t equals 0, you have a pulse A, single cycle, so you have just like one period, one period, and the period is like picosecond. And t equals tau, you have your pulse B, which is collinear with pulse A. That's why we say the spectroscopy is coherent. So you have some lags with some delay. And then after that, you at t equals tau plus t, you measure the magnetization basically at direction alpha due to the effect of pulses A and B. And the thing to look at is and so this is the first cycle of experiment. The second, you can also remove, you measure the same thing. With only one of the two pulses, A or B. And you get, and then the nonlinear response of the system would be M alpha AB minus M alpha A minus M alpha B. Right, and then you do a Fourier transform. So this thing will be dependent on both tau and t. You do a Fourier transform, you get a two-dimensional frequency diagram. Okay, and theoretical modeling. Since the pulses are so fast, you just model them using delta functions. With B can be in the direction of theta. T is B at time 0. This is a pulse A. This is a pulse B. And your magnetization in the direction of alpha at time tau plus t. It's just a Hubble formula. I1 t minus tau plus t minus t1. T1. I also include the higher terms. T1, T2, type 2, plus t minus t1. Comma, tau plus t minus t2, multiplied by B beta at T1, B beta at T2. And third order, which will be important. T2, D3, imagine you have pi3, and 3 things, and 3 things, 3 B fields. But there will be 2 such terms. Later, yeah. So this is the magnetization, and after subtracting the single pulse results, yes.
Sorry, this Taiwan is Taiwan alpha beta or something?
Yes, great.
And this,
Taiwan alpha beta, yes.
the second, this thing, this is and so on.
Yes, alpha beta beta,
Okay.
alpha beta beta beta.
Right.
Thank you. And you plug in the delta functions, your B field into the second equation. You get your M alpha and L alpha C. B pi to alpha beta beta T plus tau. B tau tau beta 0 beta plus 2 chi3 times. With different types. T, alpha beta 0 beta squared. I should have pasted this equation onto a slide. So this one couples to the T equals 0 pulse quadratically, and the T equals pulse linearly, and this is the other way around. Okay, now we're going to the transferability model. You can do a Jordan-Wigner transformation of the space. Now you get like quadratic formulas. Everything can be solved exactly. And basically, you just have for each moment of K, you have a 2-level system. The level corresponding to whether the spin-on is present or absent. And you were to choose your, so the setup would be like J exchange, ZZ, and you have a transfer field X. And you will be interested in the B field in the X direction, so the B X, because this thing will excite your domain walls. You're in the ferromagnetic ordered phase. And for this one, the spectrum dispersion is X squared plus H squared plus 2JH. Okay. And then you can calculate everything. Chi1 X. So you're also detecting the X direction. The arbitrary time is you just, so it can be expressed as some commutators of magnetization at different times. And in the end, the result is just Heaviside theta function divided by system size, summation over momentum, sine squared theta k, where theta k is theta k. Theta k is arc sine minus 2j sine k over lambda k. Some function of j and h and k. Sine squared sine 2 lambda k t. So if we do a Fourier transformation, this one will give you some delta omega minus 2 lambda k. So, and you have this summation over k, that gives you the broad continuum. Right. And now if you go to second order, two. X. It's like some commutator of magnetization as well, and it's like a 3-point. Okay, let me just write it. In the end, it's just computing some 3-point correlator of magnetizations. Okay, and the result is from theta summation over k again. Sine squared theta k. Sine theta k. This is the most important part. 2 lambda k tau minus cosine 2 lambda k plus tau. This one only depends on tau and is not oscillating in the capital T. So it will be it will give you a signal of at omega capital T being 0. So this is what people typically call it terahertz rectification signal. It's just an A because it's independent of T. Right, and this one will be oscillating. And it will also have some broad thing. And now at third order, something interesting will happen. I think that one I didn't call oscillator. Right. So third order, you have 3 different types. And turns out, so these are heavy side data, and it has 4 terms contributing at each momentum k, and they look like this. In particular, recall we have 3 chi3s contributing to the third order signal. And the first one, chi3, E equals tau. It has again 4 terms, and it has A1 at k proportional to sine 2 lambda k tau plus E, more or less similar to the previous one. A2 proportional to sine 2 lambda k tau. Again, some rectification signal. AK3, not interesting, similar to AK1. AK4 is the most interesting thing. So let me write in a separate book. Sine 2 lambda k T minus tau. So the minus sign here. Namely, when you have your measurement time, capital T equals tau, you get no phase accumulation. So whatever phase that you accumulated in the first time, you will be canceled in the end. So that's why what people call this spin-on echo. And this is the echo for arbitrary momentum k. And if you do a Fourier transformation, this will give you omega tau equals omega t. So it's like a line in a 2D frequency diagram.
This echo is specific to the transversal field acting model or generic?
Generic for it. Later I will mention is for arbitrary equivalent width. Right. And this is one component of chi3. The other component of chi3. This A1 and A2, A1, A2 are not interesting. They're the same as above. A3 and A4, both proportional to sine 2 lambda k capital T. So this one is independent of tau. You will see omega tau equals 0, the line of signals along the omega capital T axis. And this one would, people call this pump probe signal. Because now it's like there's no delay between 2 pulses, almost like just 1 pulse, and then you have some detection, so it's pump probe. And do I have a video for this? Yeah, okay. Let's look at the first row. Linear susceptibility, imaginary part, you can also see my cursor. Right. So you have the broad continuum. Second order, you have this rectification. Yes, the rectification signal along this line at omega capital. Sorry, this is whenever you see small t is actually capital T. So it has this omega capital T being 0, this line of signals, as I mentioned. And when you look at chi3, now we have this horizontal signal corresponding to omega tau being 0. And also you see this spin-on echo, this diagonal thing. Right. Now this is the ideal case. When you have some, you can also consider a case with some perturbations. Say you have maybe some disorder or something, and now you have finite lag times. You have T1 to the population time. You have T2 to the decoherence times. And you can still compute all these chi's. For chi1, where's chi1? Yeah, it's here. For chi1, you will have a modification. So basically, in addition to this, so now you have a broadening of the delta function. This is some Lorentzian, and the width is 1 over T2. But you're already broad, so you cannot see anything. It's only a quantitative change.
Decoherence.
Decoherence. And now at chi2, you see something like this term gets a correction of T to the minus T over T1. This term gives you T to the minus T plus tau T. Nothing interesting again, just some broadening. Chi3, let's look at the spin-on echo, which is the most interesting part. This one will give you a fraction of e to the minus t plus tau divided by factors between. Important thing is this is t minus tau, this is t plus tau, they're independent. So this one is like this signal along the diagonal. And then when you have some disorder, you have broadening of this thing in the other direction. So basically, by like looking at the spin-on echo, you can directly observe this capital T. So that's how they can extract the intrinsic property of the spectrum. So that's the transfer field lazy model.
What is
Yes.
population time? What is happening?
Why is the model studied here? So,
Transfer field lazy model.
I see.
And it has domain walls. So the domain walls are deconfined. So they can be viewed as some kind of spin-ons.
Yeah, so is there any symmetric constraint for the non-zero segment and
Sorry, non-zero what? Getting non-zero what?
non-zero response? Is there a symmetric constraint?
There could be, for example, if you have some centrosymmetric material, you probably don't have chi2. Later when we will discuss collapse spin liquid, you don't have chi2 either, but I will discuss.
So this way of thinking about effects as analysis kind of specific to 1D. That's kind of why.
Specific to 1D, yes.
I see. So that's why you can kind of get an equidance with that.
Yes.
But that is a bit fine. You're trying to see that some of these features are universal, also applies to.
Some of the features are universal, in particular for spin liquids. You also get a spin echo, and what's important is this thing will pass through the region. It will have zero intercept. I will mention later.
What has a population time?
So I think in an ideal case, T1 is infinity, and population is probably just the lifetime where the spin-on exists. Let me go to Kitaev. Where's my notes? Okay. Now spin liquid. They look at the case of isotropic parameters. And now recall when we compute chi2, it's actually looking at the 3-point correlators. And they write it in a convenient representation. So let's say we want to compute. So now the field is in the z direction. So MZ. Okay, this thing. One can insert some resolutions of identity. KL PQ G sigma Z J P sigma Z K Q sigma Z. Oh. G is a ground state, PQ are some intermediate states. So when you act sigma Z on the ground state, this thing does not commute with the plaquette operators nearby. So say you act sigma z on this, it will create some two fluxes at the nearby fluxes. Yes.
Oh, sorry.
Oh, okay. Right. Okay. So this one has zero flux. This one has two neighboring fluxes. This one, since it's connected to the ground state, it also has to have two neighboring fluxes. Wait. But yeah. Wait. Yeah. Right. But these two things cannot be connected by a sigma z. So that's why the chi group has to vanish in this case. Right. And let's look at chi3, which is some more interesting stuff. Okay, let me also write, so chi3 is like a 4-point correlator. MZ0, MZ tau, MZ. This is one example that appears in a calculation of chi3. So, okay. Summation JKLM PQR. Oh, I'm sorry, I'm missing some very important thing. So there's a phase factor of I, ground state energy minus P times what's T plus I EP minus EQ times some other T prime, something like that. And right, so now we have G. Just instead of writing sigma, I'm just writing the ingredients. P, E, K, Q, Z, L, R, Z, M. Ground state. And some phase factor as a function of times. Okay. Now this thing, again, it has to be two neighboring fluxes. Similarly, this thing has to be two neighboring fluxes. This thing, Q, can have several possibilities. Either it's annihilating this two flux, or it's well, if it's annihilating, then this whole thing is just a product of the 2-point correlators. Or you can have just 4 flux that are separated from each other, like 2 pairs of fluxes, or it can have 2 non-adjacent fluxes. Right, so it's like originally you create some fluxes here, and second step you act Z here, and you are annihilating this one while creating another one. That's the state Q. Okay. Let's take this as an example first. After you do the Fourier transformation, what you get is still summation over PQR, some delta function. E0 ground state energy minus E2, the energy of 2 fluxes, plus epsilon P, the energy of some matter fermion, the Marana C fermion. And times delta function, omega capital T plus 4 flux energy minus 2 flux energy minus epsilon R times the matrix elements, but simplified. Okay. DJ, E, P, CK plus CK, P, CJ, parenthesis, Q, CK, R, CJ. And you can observe from the delta function that you will see no signal between the following interval. No. This is nothing but a Smirnov gap. So from this nonlinear spectroscopy, you can extract the gap of your fractionalized excitation. And for simplicity, let's take, I don't know, the epsilon r to be the same as epsilon p, because they're both the two flux states. And just solving these two delta functions, you can get a peak at omega tau equals E0 minus E2. And you can get omega tau equal to E2 minus E4 plus epsilon. And this is minus omega tau E4 minus 0.
So here is a Jx equal to y equal to z. So
Yes.
gapless primitive.
Gapless.
So it's a spinor gap and the gapless.
Oh, so sorry, it's the gap for the flux. So in a gapless phase, it's the matter fermion that is gapless. The fluxes are still gap. Right. So you can solve for omega tau and omega t, and you will find if they're the same up to a sign. Then, oh, okay. Right. And this thing corresponds to the R3, the green R3 in this figure. And if you extrapolate this thing near the origin, you will see an intercept of E4 minus E0. So this can also somewhat measure the flux gap. And now we're going to look at spin-off echo. So this is the case where I've chosen Q to be 4 flux. If I choose the Q to be 2 flux, where corresponding to a lengthening of the string of fluxes, you will get similar some delta functions times matrix elements. Right, yeah. Plus 0 minus E2 plus epsilon r delta omega t plus E0 minus E2 epsilon. Right, now for example, if you also take this simple case, you will just get omega t equals omega tau. For when omega tau is larger than the gap. This corresponds to this little vague lines. They have 0 intercept. And the meaning of this thing is just your flux string has 0 tension. So that's the signal of deconfinement. So in a 1D easing, it's the same. So this one has like 0 intercept. If you look for the same calculation for 2D easing, you will see a finite.
How do I relate the intersection to the tension of the string?
So where is my 4 flux? Right, that's it. Right, so that's it. So how do you relate the 0 tension? Oh, this this is the process where your Q has like 2 flux. So you're lengthening the string, but you don't have energy cost. Basically, which can already be seen from here. They're both E2, not E2 prime or something. So there are multiple correlators, 4-point correlators that will contribute to this chi3, and altogether they sum up to this diagram. Where you can also see this like strong signal right beyond the spin-on gap, the flux gap. Okay, so there's also some theory paper on power code and fractals. Power code is more or less the same as here. You have some signal of deconfinement because anyons are like anion strings are tension related. For fractons, if you look at say XQ model, it has some planons. For planons, the story is the same as here. For lineons, it has some one-dimensional mobility, and this thing already has some signal in linear spectroscopy. It has some like diverging density of states near the band edge, but then this need to be combined with some other experiments, say transport, which is we need to use that to confirm that this 1D signal is not due to some intrinsic anisotropy of the material or something. And if you have type 2, say Haas code, in that case, if you apply a single, say poly X or poly Z excitation, you can create a 4, yes.
Oh, sorry,
four fractons bound state. And this thing, to really see some sharp signal, you need to go to even higher order of susceptibility, which is unrealistic.
Right, so I guess similar to the 1D case where the symmetry breaking state kind of plays as a toy model for deconfinement, right? Because the domain laws are deconfined. I guess similarly, you could think of domain laws and subsystem symmetry breaking as being fractonic. You see what I mean? Like you know, the domain laws and subsystem symmetry breaking in 2D can only move along lines.
No, I'm not following.
Oh, so okay, basically. Like in 1D, we can do deconfinement
Yes.
at the expense of looking at symmetry breaking states, right? I
Yes.
think domain laws.
Yes.
Similarly, if you want to look at fractals in 2D, effectively, fractal deconfinement in 2D,
Okay.
we look at a domain law of subsystem symmetry breaking.
Okay. Are they like deconfined?
Are they not? Sounds like they would be no.
Okay, then it will have similar signals.
Yeah, it sounds like a similar case to study for a whole Kishore. Like you
I
can
see.
say to the 3D fractals, but I guess similar to the one. Right? So it sounds like.
So you mean it's easier for like theoretical calculation or?
I mean, it sounds like a simple toy model. But
Sure, okay. Yeah.
Or is there some fact? I don't know.
Yeah, I think it will work. Yeah. So these people considered, in addition to the exactly solvable point, they also consider some like dispersion, some perturbations. So that's why the signal looks like a little weird. So this is some experiment on the conventional spin wave. Just one page. So this thing, I don't know how do you call this? Yttrium orthoferrite something. So it has a candid magnetic order. And the spin wave has two modes called AF mode and F mode, basically corresponds to different directions of oscillations. And these two modes have different characteristic frequencies. And then, well, this is just to show that in the experiment, they can really do this. They can get the 2D diagram with all these signals, like with the names that I have mentioned. This is a terahertz rectification signal. This is some pump probe signal. And this is some second harmonic generation. This is the Chi2. Some phasing, not like refacing, stuff like that. So all the fancy names just correspond to different components that contribute to Chi3. So this column is for AF mode, F mode, and this column is numerical simulation. They match pretty well. And these are some one-dimensional, like extract some one-dimensional data from this two-dimensional figure. And left bottom is just to show they can they can identify which signals are second order, which signals are cubic order, by looking at the strength of the signal with respect to the pulse strength. So that they fit pretty well.
This model has fractalization?
No, nothing, just conventional signal.
Okay, so there's no spin angle.
No. Right. Okay, so take away message, just spin on echo. Some diagonal thing with zero intersection. Yeah.
So this zero intersection will be robust under this order and others.
This bottom, this thing is this order. So this is ideal finite lifetime with this order. That's pretty well. I think there's also the Torah code paper also presents some other disparate I think disorder or some other perturbations, and it's also well, everything is blurred, but you can still see the zero.
Probably there should be some words that guarantees.
Some what guarantees?
There's maybe some we can prove with it. That's the first video because of some rules. Yeah.
Yeah, so this is if this is a measurement of tension, then if you're deconfined, you should Yeah.
Should be approved.
Yeah.
Mhm.
Okay, almost finished within 30 minutes. Okay, let's thank myself. Let's meet again in 2 weeks. Next talk will be about STM.
Yeah. And